pull up my shit. Two. Okay. All right, so boiling point and melting point. There are basic trends that we need to keep in mind. Someone tell me one of them. What's one of the trends that we need to keep in mind for boiling point? I mean, I clicked record. The longer the chain, the higher the melting point or boiling point. So one of the first things that I would personally look at is hydrogen bonding. So the more hydrogen bonding that there is, the higher the boiling point. Because we know that from Gen Chem, we have those intermolecular forces, right? Yeah, those IMFs, as we often write them as. So something to keep in mind is that the more hydrogen bonding that there is, the higher the boiling point. And a perfect example of these are things like ketones, or any carbonyl and alcohol. So looking at these two, based on what I just told you about hydrogen bonding, which one of those would have the higher melting point, the higher boiling point? The alcohol, yeah. Because this ketone, although that is an electronegative atom and it has the ability to hydrogen bond, it is not hydrogen bonded. Carbon bonded to an oxygen is not associated with hydrogen bonding. It has to be an electronegative atom bonded to a hydrogen. So yes, the alcohol would be correct in saying that that would be the higher boiling point. All right. And so something else to keep in mind is cis and trans. So don't assume oxygen has a hydrogen if it's negative. This oxygen is not negatively charged. It is double bond. There's two bonds coming off of that oxygen. It is neutral. It is not bonded to that oxygen itself, isn't bonded to anything else. And so in order to have hydrogen bonding, you have to have an electronegative atom bonded to a hydrogen. So something like oxygen or fluorine, or what's another one that often occurs in biology, chlorine. So things like that, an electronegative atom bonded to a proton, i.e. a hydrogen, will be a hydrogen bond. I could do some recording out today. Actually, you know what? Since this is recording and so I don't get a spam of emails, I've posted all my sessions except Tuesdays on YouTube. And so to do that, I will, and so yeah, to not have a flood of emails or to email 15 of you individually, I will post this recording on the YouTube that I've always used, and the link to that is now in the chat. All right, so going back, cis and trans, all right, there's nothing different between the left and the right one but the cis and trans, all right? Does anybody know what would create the higher boiling point? Somebody saying it privately, someone shy. It would be, yeah, it would be trans, all right? Because that dipole, right? The more dipole that there is, the higher the boiling point, all right? So that should be relatively simple. If you have a double bond and you have something that is cis, that will be a higher boiling point than that of trans, all right? Another thing to look out for, again, these are basically the same thing, all right? These are both carbonyl groups. These are both alcohols. Looking at this group on the left, which one is more, which one has a higher boiling point? Someone says the one on the right, someone says the one on the left. Yeah, the one on the right, all right? Because even though there's that dipole that cancels out, what do you need more? If you have more hydrogen bonding, those hydrogen bonding, that's strong as shit, right? So you need more and more heat to break up those hydrogen bonds. That's why the one on the right, again, the more hydrogen bonding that there is in a molecule, the higher the boiling point. All right. These two. What about this one, left or the right? The left, yep, the left one is the only one that has hydrogen bonding, all right, because of that alcohol. That this oxygen here is not bonded to a hydrogen, all right? There is no hydrogen bonding in this one on the right, all right? And so trans has a higher boiling point. Yes, Alexander, going back to someone, the Casey that asked cis. So if you, cis and trans is often going to be referred to when you're dealing with something like a double bond, or like E and Z, for example. If you're dealing with something like this, cis will always be a higher boiling point because of that overall dipole. Wait, you mean trans? No, trans has a lower boiling point because the dipoles cancel out. So cis has a higher boiling point. And so one may ask, what about melting point? Which is a perfect example, all right? So this one, you've probably seen it on a quiz. I do. If you're one of my students, you know I pull from some quizzes that I've seen before. So with that aside, which one of these would have the highest melting point? Does anybody have any idea? Sam, in terms of the distribution of topics, I heard that the people that took it today, there was no mass spec, and I didn't hear about NMR, but from taking this course before, I with confidence would say that you're not going to see anything more complicated about NMR than you saw on exam 3. So people are saying C. All right, so why? Why are you guys saying C? I think of ice, branching, not branching, although that is associated with melting point. So one thing that you can think of is basketballs or books, right? What do you know about solids? Solids are things that are compacted, right? They're highly compacted. There is not much space in between those molecules, right? So if you were to stack a bunch of books, right, books are flat. They aren't sphere-like. You can easily stack them, creating an overall structure, right? In this case, a solid. In melting point, if you were referring to melting point, you're going from a solid to a liquid. All right, so something I think about is if you were to stack baseballs, right? If you're to try to stack baseballs on the fucking floor, right? You can't, right? They're sphere-like. They'd simply just fall apart, right? And so which one of these is sphere-like? C. All the other ones are planar, in which you can easily stack. Does anybody understand that analogy? Does that make sense? So with melting point, you are looking for, so some people in the chat are correct. You are looking for more compact, you're looking for branching. And of course, with both melting point and the stronger force. The key to this, I would say, is sphere-like. So the more ball-like it is, the more you're not able to stack on top of each other, and thus it'll easily fall apart. So hopefully that made sense. So that's too complicated. There was IR on the exam. Does anybody want me to brush over IR? Sorry, so which one was the melting point? All right, so here, I'm gonna write it out. So melting point, let's go. More branching. More sphere-like. Thus, less surface area. Boiling, of course, that is stronger the forces, so it's easy to look at hydrogen bonding. More surface area. You guys got me on that one. All right, so to reiterate, if you have something that is more sphere-like, just going back, if you have something that's more sphere-like, not planar, more sphere-like, right, you would have, they would easily fall apart if you cannot stack them on top of each other, like that analogy, Sam says baseballs, unlike books, all right? So if you can stack them easily, more energy is required to melt it, all right? If they're more sphere-like, less energy is needed to melt it. In this case, when we're talking about energy, we're talking about heat. All right, so does anybody want me to go over some IR? All right, so IR, here's this. All right, and so this is my go-to. All right, so what's the answer? All right, so based on what we were saying before, does anybody have this answer? What is most likely to stack on top of each other the best? So if you're more sphere-like in this example here, C is very sphere-like. It's just like a baseball. Can you stack those?
Hey, Michael, I think it's a little confusing because we see like descending order and ascending order. So I'm like looking at an example for melting point and it says descending. Is that going from the lowest melting point to the highest melting point? Is that what that means by descending, or going from the highest melting point to the lowest?
Descending? I don't know what you're referring to.
I don't know. It's just what the questions say.
No, that would be highest to lowest, because if you're descending a mountain, you're going from the top to the bottom.
So like the highest energy it takes to the
Yeah, if you're okay, so yeah, if there was a question like descending melting point, then you would order it in the highest to lowest.
So the highest energy it takes to the lowest energy it takes to melt something.
Yeah.
Okay. From the example I have, they have something like C ranking it as the highest then.
Okay, and so going back to A and B, which one would we say is a higher melting point? A or B? Someone said A, someone says B. So they're both ring-like. But what does B have that A doesn't? Hydrogen bonding. Yeah. All right. So the stronger than molecular force, man, I'm struggling to say that, applies to both melting point and boiling point, because the stronger intermolecular forces that you have, the more energy that you need to apply. All right, so somebody did say that they want me to touch on IR. I would say it's safe to simplify it to this. All right, I would assume that you are going to get a table which would look something like this, but this does not tell you the shape of it at all, does it? All right, so if you're given where they're located, what do you need to know? The relative shape of them, correct? And this is what this will do for you. All right, so the OA, I've always just remembered 3 of them. All right, I've always just kept in mind 3. And those 3 are the carbonyl, the C double bond O, the alcohol, and the amine. All right, so in between 2000 and 1500, if you have anything, if you want to use analogies like a ice pick, all right, since it's cooler out. Anything like an ice pick in this range will indicate that there is a C double bonded to an oxygen somewhere in the molecule. That does not mean it has to be a ketone, all right? It could be a carboxylic acid. It could be an aldehyde. So this is just telling you, IR is simply telling you that there is something present, all right? So if you have a shape like this in this range, that tells you that there is a functional group of a carbon double bonded to an oxygen in the molecule. All right, and so similarly, if you have above 3,000, a big swooping, I guess you can call swell, all right, that indicates that there is a OH present, all right? So it does not matter if it's a primary, secondary, tertiary alcohol, it can be a carboxylic acid, all right? All of those are still OH bonds, all right? So that just simply tells you that there is a OH present in the molecule. So for example, all right, so this molecule here, what three major stretches or significant stretches do you expect to see? Or what's the giveaways for this molecule? Yeah, the red and the blue, right? Because this amine is probably gonna get camouflaged into the alcohol, but the ones that you would have to definitely keep in mind are this carbonyl, which it would be very obvious, all right? It would be just like this on the spectrum, all right? And this OH, which would look something like this on the spectrum, all right? And to show you an example, all right, you see this molecule here, this hexanoic acid, all right? So to draw that out better, all right? Where do you see the two major stretches? All right, there's an alcohol in this, right? All right, what's the range of OH? Range of OH is 3,000 and up meaning this way. All right, so the telltale signs for this, if you didn't have the spectrum at all, so the thing that you would have to look out for is you see that there's a carbonyl, right? You see that there's a carbonyl. So you know that there's going to be something that looks like a big ice pick in around 1700. Do you see that in the spectrum? Yes, right here. All right. You also see that there is a alcohol. All right. What do you expect, and where do you expect that to be? You expect something low and broad, above and around 3,000. Do you see that in the spectrum? Yeah, right here. All right. So it's all so IR is a matter of recognition. All right. So I would expect him to ask something like I would expect him to give you a spectrum and give you your choices of molecules and ask you which one of these is for this spectrum. All right, you mind going back up to the chart? Yeah. Good, Maria? All right. So again, it's all a matter of recognition when it comes to IR. All right. A lot of people tend to overthink it. Don't. All right. So yeah, That's the benefit of that little chart that I have there, all right, is that it shows you the relative shape of the peaks, all right? So all you have to do is remember 3 or 4 of them, and you're probably pretty much set for IR, all right? So is there anything else in chapter 2 that you guys would like to touch on? Functional groups. Does everybody know the difference in classification between alcohols and amines? All right, and so I made this analogy before. You can think of classifying alcohols the same way that you would classify a leaving group. All right, so say you have a reaction. All right, we're going to go to reactions. Don't worry. This is your leaving group, right? Is this leaving group primary, secondary, or tertiary? Casey says secondary. Yep. So that alcohol is secondary, right? It's bonded to 2 other. That carbon here that it's leaving from is bonded to 2 other carbons. So you can think of classifying alcohols the same exact way as if you're going to classify reaction substrates. All right. So what reactions? 6, 7, or 8? Also, somebody still, what about amine? That is direct attachments, all right? So how many carbons is that nitrogen directly attached to? All right, so this one, for example, no, not including H. All right, so this first one is directly bonded to how many carbons? 1, so it's primary. This is directly bonded to 2. All right, this is directly bonded to 3. All right. So everybody clear on the distinction between classifying alcohols and amines? All right, I would assume so. So what chapter? 6, 7, or 8? Since people mentioned reactions. 6, 7, or 8. Substitution, elimination, or addition? Let's go with 7, since in my personal experience, people struggle more with elimination. All right, this one. I'll give you guys maybe 30 seconds or so. Try to give me what you think this one is. Someone says Sn2. E2. Yes, it would be an elimination. All right, so let's walk through it. All right, so is the substrate primary, secondary, or tertiary? Secondary. All right, is that nucleophile / base strong, weak, and if so, if strong, what category of strong? Strong, or strong, weak? Yep, it would be strong. So going back to our handy dandy chart, secondary, strong, secondary, strong is an E2 reaction. All right, so let's walk through this. I know this all happens at once, but I'm going to draw it out. All right. So there's a caveat with E2. All right, what is that clause that we have to keep in mind? Something about what hydrogen to take. Yep, it has to be anti-coplanar. And to the people that tend to overthink it, trans. All right, so that leaving group was dashed, right? That leaving group was dashed. That means you have to take a hydrogen that is wedged. All right, so let's draw out our possibilities. Here is a methyl, the implied hydrogen would be that. And here's just a CH2, in which these are hydrogens. All right, so for simplicity's sake, I'm just going to say beta 1 or beta 2. All right, which one will that nucleophile base take? 1 or 2? It would take beta 2, right? Because beta 2 is the only one with the hydrogen that is trans to what the leaving group was, right? That's that clause with E2, right? You have to take that anti-coplanar hydrogen. Is this one on beta 1 trans to what the leaving group was? No. So what you're going to be bonding with, or what you're going to be taking away, is what's on beta 2, and thus that's where your double bond is going to be made. So what's our answer? 3. All right. Does that make sense? All right. Let's just say it was E1, hypothetically. All right. Let's just say it was E1 for clarity's sake. Does E1 have a preference for anticoplanar or not? No. What is its preference for? You're trying to make, yep, stability. You're trying to make the most stable double bond. All right, so looking at beta 1 or beta 2, again, if this was E1, where would the double bond be made to create the more stable double bond? Beta 1, right? Because this double bond is what? Starts with an S, is what than this? Substituted. Yes. All right. The higher the substitution, the more stable it's going to be. All right. That's the thing with E1, all right? It's all about stability, all right? Here's another one, all right? I don't know if it showed up on the exam, but just to go over the possibility of him showing this molecular condensed form, all right? So what do you have to look out for? All right, so we know this tosylate is our leaving group, right? What is our leaving group? What's our classification? Alexander's is secondary. All right, and so are we going to have an elimination reaction? How do we know that? Our chart, right? Secondary, and what? What does this base fall into? What category? Casey says strong. Yes, strong, strong. All right, secondary, strong, strong. What type of reaction did we say that was? E2. All right, so we don't have to worry about creating a more stable double bond, right? We don't have to worry about taking an anticoplanar hydrogen, all right? So all we have to do is look at the size of the base. Is that base big or small? Small. So the smaller things can fit into more crowded spaces, right? Does that make sense? And what do we know about, and what's our analogy from that to organic chemistry? The more substituted something is, the more crowded it is, right? So a nucleophile base can fit into something that is more and more substituted than a big one, right? And so what is more substituted? Beta 1 or beta 2? Someone other than Casey. Yes, beta 1. All right, so that's going to be where our double bond is formed. So what is our answer? Certainly not that, because that would be a substitution. There is a reaction. All right. A or B? Yes, A. All right. So does that make sense? All right. I know Casey already knows this because she's one of mine. All right. I mentioned it before, but a quick rule of thumb that you can use is if you see an alcohol and you have an acid, this percentage is weird. Don't worry about it. All right. If you have an alcohol and an acid, it's an E1 reaction. All right. It's going to dehydrate. It's going to be E1. All right. Just to get that out of the way and get it into your head. If you have an alcohol and you have an acid, it will be an E1. All right. So that is going to leave all right. So somebody mentioned it before. E1 focuses on what? What do we need to look out for? With E1, stability, right? Let's say, all right, so stability. Can that carbocation become more stable? Yes, right? Through a shift. What kind of shift? Methyl shift, right? So there's this extra methyl that can come over and donate. and your new, I'm just doing green, your new carbocation is this. All right, so now you can create a double bond. All right, and again, you have options. All right, let's go 1, 2, 3. Again, we're talking about stability. What will create the more stable double bond? 1, 2, or 3? 2, right? So what's our answer? Yep. Okay. That makes sense. Does everybody understand the rationale when walking through it? All right, you guys often look at reactions and suddenly panic and always tell me that you just blanked, when really, just trust yourself, walk through it. All right. So do you guys want to go over a little bit more of elimination, or do you guys think you're all right and want to go to something like addition? Casey, the major product will always, that's what the table will always tell you. All right. So with the table, for example, okay, so if you notice this trend, tertiary substrates tend to have a major and minor. All right. And this table will tell you that. All right. So for example, tertiary strong, you have an elimination reaction. And so all you have to do is look at which of the leaving group is if the leaving group is good or bad. All right. And another thing, if you're choosing between a substitution and an elimination, we know that heat will always influence an elimination. All right. So there's little things that you can pick up like that. All right. All right. So elimination. Addition. All right. And so is there anybody that's not one of my students here? All right. All right, so I will drop this in the chat. Chapter 8. Where's my week 8? Week 8. And you're welcome. Here's the solutions. All right. So is addition 6 or 8? Addition is chapter 8. All right. It's basically the exact reverse. Mechanistically, it is almost exactly the reverse of chapter 7. All right. So let's look at it. 8. All right. Well, I just sent you chapter 8. I meant that you sent chapter 7. Those that have no idea what I'm talking about, look at the chat. All right, so chapter 8. Let's get it. So this handout, if you look at the handout that I dropped for chapter 8, you will see that I already categorized these reactions for you guys. All right, so if you were to flashcard, which I highly recommend you guys do, is flashcard. All right, so you're given your reagent. Your reagent, I feel like I've said this 100 different ways. Your reagent will tell you what kind of reaction is going to occur, the name of it. And what does the name tell you? The name tells you what's going to happen. All right, so a lot of these, more than half of these names are in and of, the reagent is basically the name. All right, so for example, hydrohalogenation, it's in the name, hydro and halogen. What do you think the reagent is going to be? An H with a halogen, right? So an H with a halogen will tell you that it's hydrohalogenation. And again, to those that look at that now, again, all of you have the handout, I summarized what's going to occur. All right, and so you just follow that. All right, all that's going to occur is your halogen is going to go to the more substituted side. All right, so 1 or 2 is the more substituted side. Which handout I posted this, which is week 8, that is directly associated with chapter 8 in the chat. Oh, I just wrote the game I was playing with. Yes, 1 will be your more substituted side. So that's where BR is going to be added. All right, simple as that. All right, so in exam 3, did he get mechanistic on you guys? Did he ask you about curved arrows for this stuff? All right, so just to go through this example when it comes to a mechanism. All right, so that pi bond is in of itself a pair of electrons, right? This HBr is an acid. What's it going to do? It's going to give up that hydrogen, just like as if it were chapter 3. All right, so that pair of electrons is going to go there. All right, so you have this carbocation, right? Now that floating around Br, what does that act as? A nucleophile, right? So it's now a basic chapter 6 that will come in and attack, and there you go. All right. Similarly with this one, that double bond will react with the H. Your carbocation will form. All right, can this carbocation become more stable? Yes, via what? Ring expansion. All right, so that's going to break. This is going to be made. And now that's your new. All right. Then another shift can, then a hydride shift can happen, and then you have your more and more stable carbocation. All right. If you were given an acid, what did I say about an alcohol and an acid? If you have an alcohol and an acid, what reaction occurs? E1, right? So if you have an alcohol and an acid, it's E1, right? The direct opposite, if you have a double bond with an acid catalyzed hydration, you're adding an OH. It's the exact reverse, all right? So there's your connection, all right? So here's your forms of a strong or weak acid, all right? It's most often gonna be a weak acid. Sometimes in the book, they'll do HA, right? So like a hydrocation, I guess you could call it, or a hydronium, or yes, S2SO4, H3PO4, those are all acids. All right, so a double bond in an acid produces an alcohol. All right, because all you're going to do is add an OH to the more substituted side. All right, so the more substituted side is the top or the bottom of this double bond. Top, so that is where your OH is going to go. And so doing the reverse, again, back with that connection, if you have an alcohol and you have an acid, then it's E1, right? You guys see that? You guys see that connection? Yeah. All right. So, like I said, a lot of things are in and of the name. What is in this molecule that tells you that it's oxymercuration, demercuration? Mercury, right? This one, the transition state. What is that transition state called? The Mercurianium ion. All right. So HgOAc2 looks something like this. All right. So all that occurs is one of these leaves, all right, and this double bonds with that mercury. Again, a lot of people were confused before. I'm just going to flip this for drawing's sake. All right, so you're now bonded to that mercury with one of these OACs. All right, this is your intermediate. All right, this is how that forms. So it's almost just like cyclopropanation, except you're just adding your mercury reagent. All right. So that is how that forms. All right. Now, does anybody know the next step? Bueller. Does anybody know the next step in this mechanism? Yep, the water attacks. All right, that was weird. All right, so the water attacks, breaks that bond. All right. Now we would be able to, if he asks you conceptually, this NABR, the BH, the NaBH4, all right, that will demercurize, that will eliminate the mercury, all right? So all it does is just cut it away. Another water is going to react, taking one of those, and thus you are simply left with an OH adding to the more substituted side. All right, so that's it mechanistically, but in simplest terms, all you have to do is remember that if you have a mercury, all right, you're going to have oxymercuration, all right, thus you know that OH adds to the more substituted side. All right, everybody clear on this? Don't be shy. Is there anybody that's not okay? All right. Halogenation. Halogenation. What do we think that the reagent is? All right, we said hydrohalogenation is a hydrogen with a halogen. So halogenation must just be what? Yeah, just two halogens. All right, so just two halogens will be a hydrohalogenation. I mean, a halogenation. All right, hydrohalogenation is a hydrogen and halogen. Halogenation just itself is only two halogens. All right, and the key to this, the key to this is anti. All right, what do we mean by anti? One wedge, one dash. What would wedge and dash tell us? That they are added in the opposite direction, right? They're added in the opposite direction. So, just like Miss Leary said, one of them can be wedged, one of them can be dashed. Wow, okay. All right. And do not be confused, all right, because he's thrown this out there on an exam before. Do not be confused. This is the same exact thing as this. All right. It's the same exact thing. All right, but you know that if you started with this and you ended with this, you know that there was a rotation that occurred, so rotate it to get back to a cis and see if it was added anti. All right, so if he showed this instead, all you have to do is rotate one of them to get back to something like what you started with to see if it was really added anti. All right, does that make sense? Caleb gets it. That makes sense. Okay. That's halogenation. Also, one more thing for halogenation. If you have a diatomic halogen, diatomic meaning two, all right, two halogens, all right, but you're doing it with water, we aren't going to add two halogens. All right, we're going to add one halogen and one OH. What takes preference to the more substituted side? Does the OH or the halogen go to the more substituted side? All right, good thing I asked. It would be the OH. All right, so the product of this would simply reflect that. That's a sucky hexagon. All right, so here we have OH to the more substituted side. All right, and here we have our chlorine. All right, and you know that they're going to be added anti. All right, so you can, just ambiguously, let's say for this example, all right, here's one of them's wedged, here, this one's dashed. All right, so with this in mind, Does halogenation produce a meso compound? Alexander says no. All right, yes, that would be right. That would be no. Halogenation does not produce a meso compound because of it adding in the opposite direction. All right, if it added Sn, all right, for example, this was almost a verbatim question on the exam. All right, let's just say this, for example. Is this a meso compound? And how do you know? Kind of just gave you away with that second question. Yes, it would be. We have that internal plane of symmetry. And let me just do the R and S in my head with the alcohol in my system. This would be R and this would be S. All right. So that internal plane of symmetry, your two each side is a mirror image, and one side contradicts the other side via stereochemistry. All right. Thus, overall achiral, and you can call it meso. All right. So do you guys see how halogenation does not produce a meso compound? All right. Here you go, Alexander. All right. Hydroboration. All right. Hydroboration will often occur with peroxide. All right, that's the go-to for your solvent. I'll show you an example of a different kind of acid, but most often you're going to see peroxide being used. And so what happens? All right, in the end of things, all you're going to do is add OH to the less substituted side. All right, so mechanistically, this double bond goes to the boron, and that's where you get your alkyl borane intermediate. All right. Now the peroxide, all right, with the help of the peroxide, all that happens really is that borane gets replaced with an OH. All right, that is why you're able to do that handy dandy trick that we know of to go from your alkyl borane intermediate to your starting material. All right, so this one is that drawn incorrectly. So with that in mind, again, that B just gets replaced with an OH, right? So what we started with, we can just cut, boom. All right, that's what we started with. All right, cut, double bond. That's what we started with. Cut, double bond. That's what we started with. You guys see that? That makes sense? So once that B is replaced, that is our product. All right. If you have hydroboration with something like acetic acid, that OH will not stay. All right. It will just be stripped away. All right. And an example of this is here. All right. Unfortunately, I just showed the answer. So what occurs? All right. So the first step is hydroboration. All right. And what do we know about hydroboration? We say we're adding Sn. All right, so let's just say this one is dashed, and we're also, there's our OH, and this is our hydrogen, all right, but in this case, it's a deuterium. Do you guys see that? If we were to just do hydroboration, this would be our product, correct? You guys see that? I mean, not literally. I mean, do you like get it? All right. So what this type, I believe it's acetic acid. It's a carboxylic acid. That all that does is just take away that OH that you added. That is why you're left with that. All right. Does that make sense? So if you have hydroboration with a peroxide, it's going to be your typical. All right, you're adding OH to the less substituted side. All right, but if you follow that up with something like acetic acid or something with a carboxylic acid, you're going to eliminate that OH. All right, does that make sense? I'm assuming so. All right, dihydroxylation. All right, that's in the name. What's going to occur? All right, what's a hydroxyl? What does di mean? As in not DIE that we want to do after this exam. Yeah, two OHs, right? So we're adding two OHs and you're adding Sn. All right. So unlike halogenation, can dihydroxylation make a meso compound if it adds Sn? Yes. Does that make sense? This was almost an exact question on the last exam. All right, and so like halogenation, be careful. This all right, this is really this. You guys see that? All right, cool. All right. Ozonolysis. Any question, comments, concern on ozonolysis? No, you guys good on ozonolysis? All right. Well, I'm just going to go with what's said in the chat. And what did I say about this one? You have an alkene and an acid. What happens? Said it like 5 times. What happens? An alkene. on a need one, because elimination, you're creating a double bond, but what's the opposite of that? What do you do when you add OH? Starts with an H. You hydrate it, right? If you're adding water to something, you're adding OH, you're hydrating it, right? If you're eliminating OH, you're eliminating water, you're dehydrating it, right? So and we know that there's going to be an intermediate, and if that intermediate can become more stable, it can. That breaks, this forms, thus we get this. Does that make sense? All right, Alexander's good. All right, cool. That is what I've asked before. All right, so also cyclopropanation. Have you guys seen that come up on the exam? Have you heard it come up on the final at all? Cyclopropanation. It goes on the quiz. All right, so cyclopropanation. It's in the name. What are you making? Making a cyclopropane, right? So, for example, let's do some. All right, all that occurs is you create a cyclopropane, you create a triangle where that double bond was. All right. Now this would be something like CH2, X2. All right. You don't see any halogens on that cyclopropane, do you? No. If you had just CH with halogens, then you would leave the halogens on it. All right, just to clear that up. All right, does anybody know that weird name that we call, that we say that this happens via? Starts with a C. It's that weird name. Carbene divalent. All right, carbene divalence is how this occurs. What that carbene divalent does is mechanistically this. All right, so this lone pair comes in, this pi bond attacks. All right, that's how that ring forms. All right. All right. Anything else on chapter 8 you guys are concerned of? IDTS. Is that short for like idiots or something? What's IDTS? Maybe I'm just oblivious. Oh. That's the first. All right. So anybody Calling once, calling twice. Anybody on chapter 8? All right, so did you hear anything about the final about chapter 3? Was there acid base? All right, so just to, because I know there's somebody in here that's not with me, I have a former exam question that I do know a lot of people got wrong when it comes to acid base. So which one of these molecules is more acidic? Yeah, just ring some bells. Probably got this one wrong on the exam. Like, you know from cardio that cardio tells us that charge, electronegativity, and things like that. All right, somebody that didn't listen to me on Tuesday. All right, Michaela says that, I'm going on left with that one, why? Why are you guys saying NO2? Is that just a guess? I'm pretty sure that's just a guess. Yeah, it would be the nitro group. And to not guess anymore, all right, so we know that that chlorine is highly electronegative, right? Which is favorable for acidity. But when you look at it deeper, you said, yeah, you guys are pointing to it, all right? What's that, what's the formal charge on this nitrogen? The nitrogen has 4 bonds. What's the, is it a positive? Yeah, positive charge. What is the first letter in cardio for acids? Positive charges, right? So that in and of itself, a positive charge in and of itself is something lacking electrons. If it's lacking electrons, it's going to want them, right? Where's it going to get them from? The ring. So it's going to draw electrons towards itself just as if it were electronegative. Not only that, but there's also these big ass electronegative groups, right? So as a collective, this nitro group is more electron withdrawing than just this halogen. All right, so instead of guessing, does that make more sense? All right, cool. All right, so we went over chapter 7, we went over chapter 8. Curved arrows with regard to chapter 3 is basically reactions. So let me pull up chapter 6. And I will also share it. So the first page of that document, if you're using your computer, you can open it up, is a summary of everything. All right. computer's about to die. All right. So substrates, primary, secondary, tertiary, more substituted. Leaving groups, bigger the better. Think of it as your, I don't know, you're holding, I don't know, you're holding somebody off a cliff, right? What are you more likely to drop? A big person or a small person? A big one, right? It's going to leave easier, right? So with that in mind, your key to this, just like with chapter 7, is the table. All right, and chapter 7 kind of puts together chapter 6 and 7. All right, so if you have a tertiary substrate, you have an Sn1. If you have a methyl or primary, you're most often going to see primary. It is an Sn2. All right. If you have something in the middle, then you just look at whether the nucleophile is strong or weak. Is it negative? Is it negatively charged? If so, then it's strong and it is Sn2. It's not, that it's neutral and it's weak, then it's Sn1. All right. So let me ask you, here are the answers for this, but I'm gonna just ask you why. Why is this on the left, why does that occur faster? Alexander's is primary. Less substituted. All right, so it's asking about an Sn2 mechanism. What do we know that Sn2 prefers? Less substituted, right? And what that means, primary. It reacts faster because it's primary, all right? This one, both are primary, but there's a difference in leaving group, right? Why does this one on the right, why is that one faster? Yeah, that leaving group is bigger, right? Because in terms of the periodic table, you go fluorine, chlorine, I believe it's I, then Br, and so on. All right. And I believe that's never going to occur. That's basically the same question. All right, well, this one. All right. So this one's from your book. All right. So both are tertiary. Both have the same leaving group. There's a difference in solvent, though. The first one occurs because it's more polar. All right, so for an Sn1 reaction, if everything is the same and the only thing that's differing is the solvent, the thing that is more polar will win. All right. So, all right. So this one, is the leaving group primary, secondary, or tertiary? Secondary, right? And is that nucleophile strong or weak? And how do you know? Alexander, yeah, that negative charge is your telltale sign. All right, so secondary strong will lead you to a Sn2 in this case. All right, so you have your chair. All right, something happens with Sn2. Something with stereochemistry, what happens? It flips, right? So if this, so what's our rule of thumb? So Alex is the only one that's here that's not one of my students. All right, if wedged is up, down is dashed. All right, so this leaving group is pointing up, therefore it's implying that it was wedged in 2D. All right, if you're flipping stereochemistry, then it becomes dashed and thus is pointing downward. That is why our product will be this. All right. Does that make sense? Okay. All right. So that is the same thing. All right. This one. All right. You know, it's secondary. Now, is this strong or weak? It is strong. How do you know? Yes, with this one, how do you know that it's strong? Associates. All right, so this is polar, right? Like dissolves like, right? This nucleophile is polar, the solvent's polar. That salt is just going to dissolve away, thus you're left with this negatively charged methoxide. All right, secondary strong is a what type of mechanism? Sn2. So what's that nucleophile going to look like? Is it going to be wedged or dashed? Alexander says wedged. Does anybody else agree or disagree? Yep, it will be dashed. Why? Because it's Sn2. All right. Sn2. And these, I shared it, I believe I shared it. Chapter 6, shared it, yeah. All right, so have you seen this kind of example before? I'm sure you probably saw it on a quiz like this one. You probably saw almost something identical to this. All right, does anybody not understand it? Does anybody want me to go through it? All right, so leaving group leaves, right? What's bigger, the OH or the BR? BR leaves. Yes, the answer to that. So, all right, now what? This hydrogen wants to become neutral. How's it going to become neutral? Takes a proton. Where's it going to take that proton from? That oxygen. All right, so now right? So now it's going to react on itself. So you have your carbocation, and this acts as your nucleophile. What's it going to do? Just as if it was something separate. That's where that ring comes from. That is why 3 is our answer. Does that make sense? All right. And yes, I believe I answered that. This recording will be on YouTube. All right, so just be on the lookout in the next few days for it. All right, because obviously I don't have your guys' contact to send it to you. So I believe I sent. So with this being said, while I'm looking for my link, is there any question, comments, concerns on reactions? If not, then you guys are probably pretty solid and they're going to nail it. All right. And just in case, here is PDF, probably specifically for Alex. That is for chapter 10. I personally have to get going, but so these will probably be than anything else. Yeah, I would say the most high yield stuff is from chapter 3, not from chapter 3, but exam 3. And did Alexis Rashad send out that his form of an exam review? If so, there's answers to it. All right. As far as I know, today and Tuesday were the last for me. All right, so if you're a student of mine, I know there's only 7 of you in here. If you're a student of mine, this is our goodbye. All right, so hopefully I helped. Yeah, I mean, just do your best, you know, have that grind mentality. Right? You know, there's no reason to look back and say, hey, I could have worked harder, because then you're just going to regret it and you know you could have done better. All right, so grind on it. All right, especially if you're one of my students, make me proud. All right, and if you have to retake it next semester, all right, everybody, you know, some people have to. There will be a good chunk that will retake it. And if you want to be a student of mine again, I will be next semester, Monday and Friday. All right. So with that being said, wish you all the best. All right. You can email me anytime. I'll do my best to get back to you. All right. That's in the chat. You have my YouTube now, so that's for all the reviews. Not the reviews, but yeah, to my weekly lectures. All right, so do your best, make yourself proud. All right, and hold your head high. All right, have a good one, guys.